record. That's what I need to do. Get myself together. All right. So we are talking about measures of reliability and measures of item goodness as indicated by classical test theory approximations. So even if you only have 10 people in terms of your survey respondents, you can always do these things. And that's in part why I think they're still fairly common, because sometimes people don't have a lot of participants. So doing a little bit of review, the two types of characteristics that distinguish items from each other, the labels will stay the same across the semester. How we quantify them will differ depending on what model we're in. But the two are item difficulty and item discrimination. So difficulty is the idea of location. So you can say difficulty or you can say severity. But it's like, for what level of the trait is this item designed for? And an item that has a high mean would be considered an easy item, but it would be called high difficulty according to the way it's labeled, which is backwards and crazy, but whatever. Item discrimination, on the other hand, we talked about briefly, is the correlation of that item with the total score, excluding that item. So I have an example planned for the end of today in which we can look at real data, a scale development project that I was involved with as a grad student, and look at these statistics across different packages. Let's see, we started talking about reliability as well. Do you remember that? The idea of using a correlation between two test scores as reliability if you have test-retest or alternate forms, but then heading into what I think is far more common because you can always do it, unlike having to collect separate samples for test-retest or a separate test for alternate forms, you can always do alpha. So I want to pick up there, I think, slide 17. So we discussed last time what a conventionally acceptable level of alpha was across fields. Somewhere between 0.6 and 0.8 was the threshold that we came up with, right? What you're going to see very shortly is that if you have a high alpha, it doesn't necessarily mean you have a good scale. It means you have enough items. If you have a low alpha, it probably means your scale is not good, though. The converse is true on that one. So alpha is a measure of reliability that other people call internal consistency. And I think that phrase is responsible for a lot of the misconceptions in what alpha can tell you and what it can't. Alpha cannot tell you whether items go together to measure one thing. Alpha cannot index dimensionality. It cannot, based on the way that it's computed. So if you're computing an alpha for a set of scale items, you already are assuming that the items are measuring one trait, unidimensional. Otherwise, alpha doesn't make sense at all. We're also assuming, without testing, that all of the items are equally discriminating, meaning that they have equal relationships to the latent trait, that they're equally good, and that they have uncorrelated errors. The good news is that I'm going to show you an alternative way of computing reliability called omega that relaxes these two latter assumptions. It's still designed for unidimensional cases, but you can incorporate into it differences in item discrimination as well as any error correlations that you need to support the dimensionality of the items. So there is a positive end to the story here. But I have to make a big deal out of this because of the prevalence of alpha in method sections for almost every area of the social sciences. So where alpha comes from is where I want to start with this. Before I dive into formulae and such, any questions or things you want to talk about? Are we just ready to dive in? I know I am. Diving, as one does, or jumping in head first, which is the only way that I can dive. So it's a more accurate description of what it looks like. My dad tried to teach me and it just did not go well. But anyway, so alpha is based on the difference between total variance and total variance plus covariance. So if you want to compute the sum of I variances, so if I have, say, 3 indicators, I can add their variances together and come up with the total variance across these things. This is a baseline for the expected amount of variation, assuming that these items have nothing to do with each other. To get the variance of an item sum, so like what would the variance be of items added together? it's not just the variance of each item, but it also takes into account the covariance among each pairs of items. So we have the variability in each item response plus the extra component because the responses are related to each other. And it's always multiplied by 2. The way that I understand this is to think of it in terms of a covariance matrix, which always is square and has 2 sides. So the relationship between y1 and y2 shows up in this square. It also shows up in that square. So it's kind of like you're summing over the entire block when you do this. So alpha then is going to basically be based on the difference between these 2 quantities as an index of the relationship. So we have the variance of y total that includes the variances and covariances, and we subtract from it just the variance part. So basically the numerator boils down to covariance. Like how much relationship do these items have relative to their total variability? And to make it even easier, you can reverse engineer this formula into this one. And this one I like even better because it shows very clearly that alpha has 2 things going into it, and that is it. The number of items, that's the capital I, and the average correlation among the items. That's it. That's it. So before maximum likelihood, before computers, you can compute this. And I think that's one of the reasons why it took hold and it refuses to leave, is because you can always get this. But the implications of the contributions of this formula is how do you make your alpha get better? You get more items. More items, it has to get bigger. The other way to make it bigger is to increase the average inter-item correlation. But it's harder to keep items as correlated and yet find more of them. The more items you add, the less likely it is that your correlation would stay the same. So let me show you a plot. I think we'll call it a figure that describes why this doesn't measure dimensionality. Here is a picture from one of the articles on your reading list. I think it's near the top. And this is, I think, the easiest way to explain it. They're comparing 2 different tests. Test A has 10 items, and all of the items are correlated 0.3. So if I were looking at this correlation matrix, I'd be like, yeah, it kind of looks like they're all measuring the same thing. They're not that related to each other, but like this pattern is consistent with some kind of commonality driving this. In contrast, test B only has 6 items. 3 of them are correlated at 0.6, 1, 2, and 3. 4, 5, and 6 are correlated at 0.6, and across the 2, they're only correlated 0.3. Does this look like it's measuring one thing to you? I don't think so. So my eyeball visual analysis says no. But guess what? Alpha is 0.81 either way. Alpha has the mean inter-item correlation in its computation. It does not have the variance across those correlations. Doesn't have it. So there's no way to look at an alpha coefficient and say that it measures 1 thing, 2 things, 3 things, because these pockets of extra correlation are not represented in the formula. So whatever you want to call it, internal consistency or reliability, alpha basically measures how many items you have. That is what it does. So let's try out some possibilities here. Given alpha, you can compute the average inter-item correlation, or go back the other way. So by the way, this will be one of the questions on one of your homeworks. This box right here, I will give you alpha and ask you to compute the average inter-item correlation. But here is a range of possibility for what alpha would be under each of these circumstances. So if I only have 2 indicators and they're correlated 0.8, my alpha is 0.89. If I have 10 indicators and they're only correlated on average 0.2, alpha is still within what we decided would be acceptable, an alpha of 0.7 in this box right here. Does that surprise anyone? When I used to teach in psychology at Nebraska, this is the point where people's heads would explode. Because it's like, wait a minute, if these items are correlated 0.2, how much shared variance is that? We take that r and we convert it into r squared.
Even less.
Even less, 4% by my math. So you're telling me that these 10 items have 4% in common and 96% whatever, and I'm calling this internally consistent? That's optimistic. Alpha is not bounded by 0 and 1, by the way. True story, a student that I was helping with a dissertation at one of my previous jobs, that lends some anonymity, I've worked at a couple different places, was working on an analysis of items that were binary, and she wanted to add them all together to create some sort of total score. And she looked at alpha ahead of time, and it was negative. And she was like, I had to have done something wrong. I've never seen a negative alpha before. Yeah, on average, that means that your items are reverse related, and you're going to add them together? Oh, that's not good. I got overruled, by the way, by her advisor, because that's what they do in their field. So she went ahead and added that up. Guess what she found with that sum score? Nothing. So if the items aren't that related to each other, putting them together into some kind of total doesn't seem like it's a great idea. So if you have a really high alpha, that either means that you have a strong relationship among your items or enough items to call it good. It doesn't necessarily mean that you're measuring one thing, the way that it is interpreted. So here is a picture of how alpha changes as a function of the number of items given the average inter-item correlation. And I give you this nugget of data. So in the GRE subtest for psychology, in the 2020 version, so this is data that was pre-pandemic, they listed the reliability coefficient for the psychology subtest as an alpha of 0.95. Alpha, when it's computed for binary items, has a computational shortcut that is known as KR20. It's a different formula, but it's exactly the same thing. So that means that an alpha of 0.95, that sounds like good, right? That's pretty high. But there's 200 items. You do the math, that's an average inter-item correlation of 0.08. So I would not call that test reliable if this is how related the items are. Yes, sir?
So because alpha can be high for reasons other than the correlation, that's why it's a problem, right? Because it's affected by the number of items.
Yes, I think that the number of items makes alpha higher. To me, the biggest problem is that this does not tell you if you're measuring one thing, which is the way that people think that's what it's saying. It can't tell you that because it doesn't pay attention to the variability across the correlations and whether there's pockets that would imply multidimensionality. That's my thing. So just having a good enough alpha is not informative, is my take-home point for this. Here is the KR20. By the way, KR20 is an expression that came from equation 20 in a paper from 1937. So yeah, these are the two authors of the paper, and this is alpha for binary items where it's easier to compute because you can just use the proportions of ones and zeros, but it is exactly the same thing. And this is how reliability is computed for the GRE subtests as well. And here's the original reference if you're interested in reading it. So one of the issues in alpha for binary items, though, has to do with this unit of analysis of a Pearson correlation. It turns out that the maximum possible correlation that two binary items can have is not 1 in most cases. It's much lower than 1 to the extent that the items have skewness. So only in the case where each item has a mean of 0.5 would the maximum correlation potentially be 1. It's much lower. So I have a table here that illustrates some different possibilities. So for instance, if you have item X, that is a very, I would call it a difficult item in that 10% of the people got it right. And you want to look at the correlation with item Y, which is much easier, 80% of the people got it right. Even if these items are measuring the same thing, the highest Pearson correlation they can have is 0.17. So using correlation, when it's defined this way for binary items, is problematic. So one of the things that is different in fitting factor analysis type models to binary items is that they don't use Pearson correlations, and it's for this reason. They use something else, which is called a tetrachoric correlation. So I have a whole bunch of words on the next slide because I wanted to compare and contrast different kinds of correlation that you may come across. So Pearson correlation is what most people think of when they hear the word correlation. It's computed using the means, variances, and covariances of the variables, straight from the data. Anyone can do it. There is a, let's go phi or phi. Do you want to take a vote on this? Anyone have a preference? Phi, phi, pho, fum. This is a correlation that's dumb. How's that? No? Maybe? I'll pretend that I can't see you smile and laugh at my jokes because of your masks and that you're really laughing on the inside. How's that? So a phi or phi correlation, depending on how you say it, is a Pearson correlation still. It's just that there's a different version of the formula. So for instance, if you do a chi-square type analysis and you ask for effect size measures with it, this is one that's given, and it's labeled as a phi or phi correlation, but it is still a Pearson correlation. Question from the audience, is there a population size restriction for computing alpha? You mean population in terms of the number of items or the number of people?
The number of people, because
Number of people.
in some literature they said that minimum number of people are 30, so I'm not sure whether this is right or wrong.
I don't know that there's a hard and fast rule for the number of people you need to compute alpha, but in general, the correlations that you're working with are going to be more precise to the extent that you have more people. So I think alpha is noisier. Like if you tried to compute like a confidence interval for it, it would be a lot wider if you only had 30 people than if you had 300. But it doesn't mean that you can't try to compute it.
Yeah.
So Pearson correlation, yeah, phi. Point by serial is another special name for Pearson correlation. And item discriminations are often called this. Like you may have heard this term in other measurement classes for the correlation of a binary item with a total score, called point by serial, but it's still Pearson. And then I have the line of suspended disbelief because the three on the bottom are different. They are not Pearson correlations. So these are words that you will see in the context of factor analysis for categorical items, IRT models, and that kind of thing. Tetrachoric, biserial, and polychoric. In particular, tetrachoric and polychoric are things we will work with in this class. And the idea is that it's trying to figure out what the correlation would be behind the underlying continuous variable that gave rise to the binary version. And that sounds crazy when you put it that way, but it actually has a mathematical underpinning that makes sense. So that'll be one of the things that we talk about when we get to categorical items. The ordinal version of that is called polychoric. So when you see these words, their purpose is to correct for the range restriction that limits the size of a Pearson correlation. And these are correlation types that you can get out of software such as R, such as SAS, such as anything. So you will get a chance to look at those as well. All right. Questions or thoughts so far? No? Cool. All right, moving right along then. Another distinction of correlation type that I want you to be familiar with, but I'm not going to spend a super lot of time on, is Pearson versus interclass. And if you're like, wait a minute, weren't you just talking about interclass correlation an hour ago, Lisa? Yes, I was. Interclass correlation shows up in the context of longitudinal data. It shows up in a lot of circumstances when you have a design where there's multiple dimensions of sampling, and you're trying to figure out how much variability has been caused by each dimension. So for instance, if I wanted to compute a reliability coefficient across two different raters, so I have two people, they're each providing some kind of judgment about a set of items for the same set of subjects. Pearson correlation as a reliability coefficient is not the right choice for this, because in Pearson correlation, it standardizes each variable to a z-score, and then it computes the relationship between those z-scores. But if one rater is systematically higher or lower, those differences are gone from Pearson. So if you want to track absolute agreement, which is what's of interest in most cases, you want to do it a little bit differently. So in this context of intra-class correlation across raters, the difference in the formula is that the two raters share a common mean and a common variance rather than standardizing for each of them separately. And then you can compute how much of the variability has to do with the targets that they're rating versus the raters themselves. And ICCs can be readily extended to more complex sampling designs. So some of you may have taken or will take the course on G-theory that we have in our department. That's this. That's what I'm talking about. You can compute how much of the variability is due to differences between items, differences between respondents, differences between occasions, differences between raters, and so forth. So if you have a situation in which you want to get inter-rater reliability, but you have a lot of raters, then just having a pair correlation isn't going to work. This will work for you. It will also work assuming that you use maximum likelihood type estimation instead of least squares, if not every rater rates every subject. They can be incompletely crossed and still come up with variance components. So just to put a place in your mind with reliability in the context of raters should be done a little bit differently. So just as a quick example, if I have two different types of data here, rater 1 and rater 2, on the first side here, they have roughly the same means and the same standard deviations across their scores. In that case, Pearson's correlation and an intra-class correlation are going to be about the same. But to the extent that the raters differ systematically, so in this picture on the right, the second person thought everybody was higher on average. Their scores were higher. And Pearson correlation and intra-class correlation diverge. So I think the question would be, do you want relative agreement or absolute agreement? If it's relative, Pearson might be okay, but absolute should be intra-class instead. And here's the formula by which the difference, it's whether this piece is in the denominator right here. So, any thoughts or questions about that? Just moving through like a tour of correlations, that's what we're doing here. All right, reliability in a perfect world. Another thing that you may come across in classical test theory texts is predictions as to what would happen if you added more items. So the Spearman-Brown formula, for instance, here is used to anticipate reliability for longer scales. So for instance, if I had a scale with a reliability of 0.4 and I have 10 items, what would it be if I had 50? This formula would predict it would be 0.77. In order for this to make sense, though, you have to believe the items are equivalent. More is better. Doesn't matter what kind or for whom, just more is better. So the assumption underlying the use of this formula is parallel items, which means not only are all of the items equally discriminating, but they also have the same amount of error variance to them. So that both of those are testable constraints in the world of structural equation models.
Yeah. Question.
Hit
What
me.
is reliability in this instance? Is it R? Is it alpha? Is it any? We could put in any measure?
Pretty much, yeah.
Okay.
Yep. Yeah, it could be test, retest, it could be alpha, it could be split half, it could be,
Okay.
yep, doesn't matter. Yep. Other question? All right, no? Okay. All right, yeah. So this idea of parallel indicators also shows up in the context of when some scores would be equivalent to latent variables. And I put out a shout out here for an article that is on your reading list like a month from now or so, but it covers this in great detail. If you're adding items together, that is the same thing as a latent trait model with a parallel items set of constraints on it. So factor score F as a predictor works out to be the exact same thing as the sum of the item responses if all of the items are equally discriminating and they all have the same amount of error variance. To get them onto the same scale requires a little bit of wizardry in terms of the constraints, but they figured out what it should be, and there's an M+ example for that. So whenever people try to make an argument that, well, these items don't go for a factor, I'm just going to add them up and make a composite, that is still a factor model. It really is. Mathematically, they are equivalent. So you don't get out of things in terms of reliability just because you're not thinking of it as being derived from a factor. It is the same thing. You might also see attenuation-corrected reliability estimates and correlations. So for instance, if I have a correlation between two variables that is 0.38, but each of them doesn't have a great amount of reliability to it, You can use this formula to anticipate what their correlation would have been had they had better reliability. And I'm not even lying, this is the example that was given in the original publication, a correlation of 1.03. Does that give anyone pause? Like that's a heck of a correction right there. However, this idea that we're going to look at the true relationship after correcting for measurement error, does that wording sound familiar? That is what you're here for. So this one example, although it's a little crazy because of the numbers, is basically the logic of doing a structural equation model. The idea is that you get a better estimate of the trait you're trying to look at, and if it's a better estimate, then the relationships across the traits you're interested in should be stronger or truer than if you're working with just a correlation that has error to the observed variables. The problem in this case is the amount of disbelief limiting reliability here. Like a reliability coefficient of 0.25, like most of that variable is error. So I don't know what it would mean to think about just the true part being correlated with something else. So the problem would be the measurement here, not the extrapolation. Another use of reliability is to figure out what standard errors and confidence intervals would be around a particular score. And in a lot of cases, people assume that reliability is constant. That means, in turn, that the predicted amount of error variability that's left over is also constant. Now, logically speaking, that probably isn't true, but it's usually a common assumption. So it would go a little something like this. Reliability is the proportion of a total score that's thought to be true. So if we flip that proportion around, we can figure out how much of the variability is supposed to be true. Well, it's the total variance times the reliability. So like 80% of it, 70% of it. Then you can work backwards to figure out how much of it then has to be error, because that's just the difference relative to the amount that's true. You can use that amount of error, take the square root of it, and then it becomes a standard error. And then you can build a confidence interval around people's scores using this standard error. So like a 95% confidence interval would be computed like this. So when does error variance matter? Would be in thinking about how much you trust the scores. So let's say that I have a variable whose total variance is 100. I've got 50 subjects. Let's say that in one case, the reliability of that variable is 0.91. That's pretty good. Well, that means that 91 out of that 100 is true score variance. That leaves 9 to be error. I take the square root of that 9. My standard error is 3. So if I have a score of 50, then here's the range around that, given that reliability coefficient of 0.9. Same situation. Now if I have a reliability of 0.75 instead, now there's a lot more error variance. Now the standard error is a lot higher, and the range is broader. So even though, like we're saying, this subject has a 50, how sure are we that it's a 50? If I were selecting people to be included in some program, and I had a cutoff, say, of 42, you have to be above 42. Is this person getting into my program? In the first situation, yeah. In the second? Could their score be under 42? It could. So then it's like, well, what do I do with that information? So it's not just about someone's score. One of the uses of computing reliability is to figure out literally how much error there is around that score, and whether that error in the context in which you're measuring would change a decision that you make about an individual person. So when might one do such a thing, like make a decision about an individual person based on a test score? All the time. So here is a plot that I made using publicly available data about the GRE. These data are from pre-pandemic 20 to 21. The link where I got the data is at the bottom of the slide here. It is now the current version of the year's results, so 21 to 22, but I kept this because it was pre-pandemic and there's less problems in terms of who got to take it and whatnot. One of the interesting things about the GRE is that a lot of programs rely on it religiously in terms of their admissions. Even though they're not supposed to, it's very common to say, well, this candidate had a higher GRE score, so we should pick them for funding first. Even in the words that go with this documentation, the people who make the GRE say not to do that. But they don't provide with an individual score report what the standard error is. So when you got your GRE scores, there was no information given to you about how precise they were. And that is, I think, in part because how precise it is depends on your score. Measurement error is not constant, and it depends on which particular items you got. But this is what it looks like if you actually compute a confidence interval using the standard errors of measurement that they estimated, and by the way, they did this via simulation using a 3PL IRT model. So if somebody who has, say, a score of 155, their confidence interval is somewhere between 151 and 159. That's quite a range in terms of what people would consider like a good enough score to get in. So this is a complicating factor in using scores about people to make decisions. Also note that the test is bounded at 130 and 170, and yet the implication of these standard errors go outside the bounds. So they probably can't be right, especially on the lower extreme ends. Question, and the year you took it since the percentiles change per score? Yes, yes, percentiles change. I'm just talking about what the numbers mean. Yes, sir?
You mentioned measurement error is not constant, and that made me think. So my guess would be it's more precise at the low end, right?
Not according to this.
Okay.
And I think that has to do, well, I know it has to do with the number of items that are available. So this is the idea of the construct map, right? Like if you want to reliably estimate someone who has very low, this is verbal ability, you need a lot of really easy items. Like the kind that I wandered into when I took the adaptive GRE. It's not adaptive in the same way anymore, but I could literally see my score tank as the items got easier and easier. Eventually it was like black is to white as, and I'm like, okay, this is not going well if this is the place where I've adapted to in terms of the test. But if you think about what the GRE is used for in terms of selection to graduate school, somebody who has a 130 is not getting into graduate school, but with this test score. So from the purposes of precision, it kind of doesn't matter how good of an estimate it is because it's so far away from what people would consider, good enough. I don't even know what the scales are because I'm still tied to the 200 to 800 scale. But in terms of making funding decisions about, who should be prioritized, well, I have a candidate who has a 151 and someone else has a 159. It's like, are they really different? I don't know. So standard error of measurement matters in terms of making decisions about people. That's really why reliability is important. But just having a reliability coefficient of 0.6 or whatever, sometimes it's easy to forget that part. Yes.
So, there's two kinds of things I see here. There's like the precision of the individual dots, right, vertically, and then there's that dotted bar.
Yeah, these are the bounds of the scores.
Okay.
You can't have a GRE score past 170, at least when this version of it. I don't know if they've changed it since then. Yep. It goes, these are the bounds. So I'm just saying like this, the confidence interval goes out of bounds, which lends some doubt to the use of the standard errors. Here's the quantitative ones, by the way.
Oh, great.
Oh, good, yeah. Well, we all know verbal doesn't matter, right? It's all about the quant. No, it's kind of the same story. So
And there's a lot of overlap.
there is. For what it's worth, I don't pay attention to GREs when I look at applicants. I look at their statement. If they can write well, if they can articulate why they want to come here, and it makes sense, that's like the most significant thing to me. How they did on their tests, okay.
Very holistic of you.
It's in part because I didn't do great on the GRE, and so I don't want to penalize someone else. An alternative perspective actually was, I heard another faculty member say that they do not pick people who got perfect scores on purpose, because to them it is an indicator of a perfectionist tendency that they probably studied all the time and took the test over and over and over again until they got the perfect score, and that kind of person is never going to turn in their dissertation and graduate. that was the rationale. That I can kind of see that. So I think I took it once because it was $300 and that was like my entire paycheck for a month working at, the Grisantes at the time. You'll get to hear more about that later. I waited tables through college. But I also thought, well, like, I don't know that I can do better. And it takes a lot of time and effort to try, and I got the rest of my classes to do. So anyway, holistic is one way to put it, but I think being able to write matters and knowing why you want to be there also. So for what it's worth. But all of you got picked, though, regardless of what your test scores, right? We all made it here somehow. All right, so summarizing then the idea of all of this indications of what makes items good or bad, none of that makes it into the model. So we can look at differences in item difficulty or differences in item discrimination, but those differences are ignored in computing a sum. So what kind of items would we need to improve reliability? More and more correlated items for alpha. The implication then is that standard errors are constant if reliability is constant, and that we're assuming everyone is being measured equally well. That can't possibly be the case. Yeah, someone else from the Zoomers say they took it once because it was expensive. Yes. Are all of the exams like that expensive? Did anyone take, like, what is it, the GMAT for business school or anything like that? No? Do we know? You did?
Undergrads in my lab taking the MCAT, and it seems very expensive.
Yeah. So then there's also an equity issue is who has the time and the money to retake this thing? And what does that say about, the resources that they have that someone else might not have? So it's a whole thing. There's actually a lot of fights about whether we should throw out test scores completely, and there's arguments to be made on both sides. So anywho.
Did the Ed Measurement Program suspend the GRE requirement during the pandemic or not?
There was one year I think we said you don't have to have it, but we did not decide to not require it anymore. I think we're still looking at those scores. And I think in our program in particular, it would be, I think it would be awkward to be like, come learn about educational testing, but you don't have to take a test to get here. Like there's a little bit of like hypocrisy to that, I think, that would make that uncomfortable.
I mean, you just outlined a bunch of reasons why testing is problematic, so.
Well, I'm describing, when I look at applicant pools, what I think is important and the reasons why test scores may not be as informative as other aspects of their application. That's my own personal way of looking at it. But other people have different opinions. Comments from the Zoomers, the GED is $160. My goodness, talk about an unfair situation there. And also English language tests that expire every 2 years. Yep, that we didn't even talk about TOEFLs and all the other things, right? So I don't have as much exposure or experience with those, so I'm not going to comment. But I probably could make, the same types of pictures, these sorts, where was it? Where to go? These pictures, I could probably make these pictures for any test where the standard errors are available somewhere if they're not available at an individual level. So. All right, yes, testing is expensive. But I wanted to show you